When people hear space and time, they usually picture two separate ideas. Space feels like the stage where things sit. Time feels like the clock that ticks while things happen. That picture works well for daily life, and it feels natural because experience trains us to think that way. Physics began with the same picture. Early scientists treated space as a fixed grid and time as a universal rhythm. Events took place somewhere, and they happened at some moment. The two ideas stayed politely separate, like coordinates written in different columns. Then careful measurement started to whisper that something deeper was going on. Light turned out to behave in a very peculiar way. No matter how fast an observer moved, light always traveled at the same speed. Walking toward a beam, chasing it in a rocket, standing still on Earth, every measurement agreed. That single fact forced a quiet revolution because speed connects distance and duration. If the speed of light stays fixed, then distance and duration can no longer stay independent. Space and time began to lean into each other. Imagine describing an event. A flash appears, a bell rings, a particle decays. To locate that event, one must give both a position and a moment. Physics discovered that these two pieces of information blend together in a precise way. Change the motion of the observer, and the split between distance and duration changes, while the combined description stays consistent. That combined description receives a single name: spacetime. Spacetime treats every event as a point with 4 numbers attached to it. 3 describe where, 1 describes when. The surprising part lies in how these numbers relate. Different observers may disagree about distances and durations, yet they agree about the space-time separation between events. Something deeper than space alone, or time alone, holds everything together. This explains effects that once sounded like paradoxes. Moving clocks tick differently. Lengths measured along the direction of motion change. None of this comes from faulty instruments or strange materials. It comes from space-time itself, assigning different slices of distance and duration to different observers. A useful way to picture it involves paths. Every object traces a path through space-time, called a world line. Standing still in space still means motion through time. Moving faster through space tilts that path, trading some motion through time for motion through space. All objects move through space-time. They simply choose different directions within it. This single idea replaces many separate rules. Instead of asking how space behaves and how time behaves, physics asks how space-time behaves. Motion, light, cause and effect all follow from that geometry. Once this viewpoint settles in, the universe begins to look less like a stage with actors and more like a woven fabric where events, motion, and measurement share the same structure. The fabric keeps its own order, quietly guiding everything that happens within it. Once that idea settles in, another shift follows almost automatically. Motion stops being something measured against a fixed background. Instead, motion becomes a comparison between different paths through space-time. Two observers moving differently are not arguing about reality. They are slicing the same space-time in different ways. This is where time stops being universal. There is no single master clock ticking for the entire universe. Each object carries its own time along its path. A wristwatch measures how much space-time that particular path passes through. That amount is called proper time, and it belongs to the object itself. Two observers can separate, move differently, reunite, and honestly report different elapsed times without contradiction. Space-time allows it. This sounds strange only because everyday speeds hide the effect. At human scales, the differences are tiny. At higher speeds, they grow. At the speed of light, something remarkable happens. Time along that path stops entirely. For light, there is no passage of time between emission and absorption. That fact is not poetic. It falls straight out of space-time geometry. Light traces the boundary structure of space-time. It marks the limit of cause and effect. Events outside that boundary cannot influence each other, not because of technological limits, but because space-time itself does not connect them in the right way. Cause and effect are not rules imposed afterward. They are built into the geometry. This also explains why simultaneity loses its absolute meaning. Two events that appear simultaneous to one observer may not appear simultaneous to another. There is no single answer to what is happening right now everywhere. Each observer carries a personal slice of space-time they call the present. The universe does not privilege one slice over another. Once this is accepted, space-time stops feeling abstract and starts feeling practical. Satellites orbiting Earth experience time differently from clocks on the ground. Their paths through space-time differ, so their clocks tick at different rates. Navigation systems must correct for this or they fail. The theory does not live in textbooks. It runs quietly inside technology. Then gravity enters the story, and space-time deepens again. Instead of treating gravity as a force pulling objects together, space-time describes it as curvature. Massive objects change the geometry around them. Paths that once looked straight bend, not because something pushes them, but because straight itself has changed meaning. An object moving freely follows the straightest possible path through curved space-time. That path is called a geodesic. Falling, orbiting, drifting through space, these are all expressions of geometry, not force. Remove all other influences, and an object simply follows space-time's shape. This explains why all objects fall the same way, regardless of mass. They are not being pulled differently. They are following the same geometry. The motion comes from space-time itself. Time feels this curvature too. Clocks closer to massive objects tick more slowly than clocks farther away. Again, this is not mechanical stress or interference. It is geometry assigning different amounts of time to different paths. Space and time no longer act as separate players. They respond together. Mass and energy tell space-time how to curve. Space-time tells matter how to move. This mutual relationship replaces the older idea of forces acting across empty space. At this point, space-time begins to sound less like a background and more like an active participant. It expands, bends, stretches, and evolves. The universe does not sit inside space-time. The universe includes space-time as part of its physical content. Cosmic expansion fits naturally into this view. Galaxies move apart not because they fly through space, but because space-time itself grows between them. No central point is required. Every location sees the same pattern because the geometry itself changes. Even emptiness is no longer empty. Space-time can ripple. Gravitational waves are distortions that travel through it, carrying energy and information. Detectors on Earth measure these ripples as tiny changes in distance, smaller than atomic nuclei, yet perfectly real. Georgetown itself vibrates. At this stage, space and time stop being containers and start being relationships. Distances, durations, motion, gravity, and causality all emerge from a single structure. Learning space-time is not about memorizing effects. It is about adopting a new way to organize experience. Instead of asking where something is and when it happens as separate questions, space-time asks how events relate to one another, which events can influence which others, how much change fits along a given path, how geometry shapes possibility. Once seen this way, many puzzles lose their mystery. Slowed clocks, curved orbits, cosmic expansion, limits on signals follow from one consistent picture. Nothing special needs to be added, Nothing hidden needs to be assumed. Space-time does not explain everything, but it explains why so many things fit together so tightly. It provides a language where motion, gravity, and time speak the same grammar. Understanding that grammar makes the universe feel less strange, not because it becomes familiar, but because it becomes coherent. The fabric does not need intention or awareness. Its structure alone guides the unfolding of events, patiently and precisely, everywhere at once. Once space-time is understood as a structure rather than a stage, another quiet consequence appears. Events themselves become more important than objects. Physics stops asking what something is in isolation and starts asking how events connect. A collision, a flash of light, a heartbeat, a thought, each is an event, and space-time organizes how these events relate. This is why space-time cares so deeply about limits. There is a maximum speed, not because motion is difficult, but because space-time geometry allows only certain connections between events. Light sits at the boundary. Anything slower can be influenced by many events. Anything faster would require skipping over space-time itself. The limit is structural, not technological. This boundary shapes reality in a very practical way. It decides what can be known, what can be affected, and what can never be connected. Two events can be close in space, yet unreachable in time. Others can be distant, yet causally linked. Space-time does not measure closeness by meters or seconds alone. It measures it by whether influence can pass. This is where intuition trained by everyday life begins to soften. Distance is no longer just how far. Time is no longer just how long. Separation becomes a question of space-time intervals. Some separations allow influence, some forbid it forever. This idea alone explains why the past feels fixed and the future feels open. Events in the past sit inside the region that can influence the present. Events in the future do not yet. That difference is not psychological, it is geometric. Space-time also explains why changing the past remains impossible. It is not guarded by paradox or mystery. The geometry simply does not permit paths that loop back in the required way under ordinary conditions. The structure blocks them. At this point, space-time starts to sound rigid, almost unforgiving. Yet it also allows extraordinary freedom. Different observers carve space-time into space and time differently, and all of them are equally valid. No observer owns the correct present. Each carries a personal frame shaped by motion and gravity. This dissolves the idea of a universal now, replacing it with many consistent viewpoints layered on the same structure. That realization feels unsettling at first, but it actually simplifies things. Arguments about who is right fade away. The rules do not change, only the coordinates do. Space-time itself does not care how it is labeled. Then something deeper emerges. Energy and momentum are not separate bookkeeping tools floating on top of space-time. They are tightly linked to its structure. Motion through space and motion through time are two sides of the same coin. Change one and the other responds. This is why energy, mass, and momentum transform together when observers move differently. Mass turns out to be concentrated energy moving mostly through time. Light turns out to be energy moving entirely through space. Everything else lies between. This is not metaphor. It is how space-time measures motion. This also explains why adding energy to a system can increase its inertia. Resistance to acceleration is not stubbornness. It is geometry reacting to energy content. Once gravity is folded into this picture, space-time becomes dynamic. It no longer sits passively while matter moves. It responds. Energy curves space-time, and curved space-time redirects energy. This feedback loop shapes stars, galaxies, and the universe itself. Black holes appear naturally here. They are not exotic monsters added by imagination. They form when space-time curvature becomes so strong that all paths tilt inward. Not even light can find a route outward. Time itself points toward the center. Near such regions, time slows dramatically relative to distant observers. This is not an illusion. Different paths through space-time accumulate different amounts of time. Clocks tell the truth locally, even when they disagree globally. At large scales, space-time stretches. The expansion of the universe is not matter racing away from a center. It is geometry evolving. Distances grow because the metric itself changes. This allows galaxies to separate faster than light without breaking any rules, because no object outruns light locally. The space between them grows. This distinction matters. It prevents confusion. Motion through space-time and change of space-time are different processes. Both are allowed. Both are measured. Space-time also stores memory. Gravitational waves carry information about violent events long after they occur. When two massive objects merge, space-time rings like a struck bell. Detectors sense these vibrations as tiny shifts in distance. Geometry itself becomes observable. At this stage, space-time stops being abstract. It acquires physical consequences that can be touched, measured, and engineered around. And yet, space-time remains subtle. It does not tell objects where to go. It defines what paths are available. Objects follow those paths not by choice, but because no alternatives exist. This removes the need for invisible forces reaching across emptiness. Motion becomes local and natural. This perspective also clarifies why space-time feels smooth at large scales and uncertain at small ones. On everyday scales, geometry averages out. On extreme scales, quantum effects begin to stir. How space-time behaves when those effects dominate remains one of the great open questions. Still, even without that final answer, space-time already provides a powerful unifying language. It ties together motion, gravity, light, causality, and time into one coherent structure. It replaces many separate rules with a single geometric idea. Learning space-time is not about visualizing four dimensions perfectly. It is about recognizing that space and time are aspects of one system that cannot be pulled apart without breaking consistency. Once that recognition settles in, explanations become easier. Effects stop piling up as disconnected surprises. They line up as consequences of structure. Space-time does not explain everything. It does not explain why the universe exists or why its rules take the form they do. But it explains how those rules fit together once they exist. And that is enough to speak about it clearly, to teach it honestly, and to carry the idea forward without mystery or exaggeration. It becomes a way to talk about reality that is restrained, precise, and surprisingly intuitive once the old separations are allowed to fade. At this point, space-time can be treated as a working framework rather than a surprising idea. It becomes a practical tool for organizing physical laws. Instead of memorizing separate rules for motion, gravity, and light, everything fits into a single structure governed by geometry. The key fact to hold on to is this: space-time provides the measuring system for all physical processes. Distances, durations, speeds, energies, and causal relationships are all defined within it. When physics predicts something correctly, it does so because the space-time description remains consistent across situations. This consistency shows up in equations, but it also shows up in experiments. Atomic clocks flown on airplanes return with measurable time differences. Signals from distant spacecraft arrive exactly when space-time predicts they should. Light bends around massive objects by amounts that match curvature calculations precisely. None of these effects rely on interpretation. They are measurements checked repeatedly. Space-time also explains why certain quantities are conserved. Momentum, energy, and angular momentum remain stable because space-time itself has uniform properties. When space looks the same in every direction, momentum is conserved. When time flows uniformly, energy is conserved. These are not coincidences. They are consequences of geometry. This connection makes space-time central to modern physics. Any new theory must respect it or explain why it changes. This applies to particle physics, cosmology, and attempts to unify gravity with quantum mechanics. Even speculative ideas begin by asking how space-time behaves. Importantly, space-time does not remove everyday intuition, it refines it. At low speeds and weak gravity, space-time reduces smoothly to familiar rules. Classical mechanics appears as an approximation, not an error. This explains why earlier physics worked so well before deeper structure was discovered. Space-time also clarifies limits. Faster-than-light communication fails not because of engineering difficulty, but because space-time geometry blocks causal connections. Absolute simultaneity fails, not because clocks malfunction, but because space-time allows multiple consistent time orderings. These limits are not flaws, they are features that keep physical laws coherent. When teaching space-time to others, the goal is not to force visualization of 4 dimensions. The goal is to communicate relationships. Events relate through space-time intervals. Paths accumulate time differently. Geometry guides motion. Once these ideas are in place, most effects feel expected rather than strange. At the same time, space-time remains incomplete. On very small scales, quantum effects become important, and the smooth geometric picture may break down. How space-time behaves under those conditions is still under investigation. Current theories work extremely well within their tested range, but they are not final. That uncertainty does not weaken space-time's role. It shows its importance. Any deeper theory must recover space-time behavior where experiments confirm it. This requirement narrows possibilities and guides progress. In practice, space-time acts as the backbone of modern physics. It connects experiments on Earth with observations of distant galaxies. It links clocks, rulers, particles, and fields into a single language. It explains why different observers can disagree locally while agreeing globally. Understanding space-time well enough to explain it to others means being able to describe what stays the same when perspectives change. Distances and times vary. Space-time relationships do not. Forces can be reinterpreted. Geometry remains. Measurements differ. Structure persists. That reliability is what makes space-time useful. It allows prediction without appeal to hidden mechanisms. It replaces separate explanations with one consistent framework. Once that framework is clear, space and time stop feeling like separate ingredients of reality. They become aspects of a single system that organizes all physical change. And with that understanding, discussions of motion, gravity, light, and causality naturally fall into place using one shared set of ideas rather than many disconnected ones.
How many times have you decided to study? Full of motivation to learn, open your material, and just a few minutes later found yourself holding your phone without even noticing, scrolling, answering messages, or thinking about something completely different. And when you finally realize it, time has slipped away, your concentration is gone, and you're left with that bitter feeling of frustration. Do you know why this happens? It's not because you lack discipline, and it's not because the subject is too difficult. The truth is, the world we live in today was designed to steal your attention. Phones, notifications, short videos, instant pleasures, every one of these things is training your brain, day after day, to chase quick rewards and run away from deep effort. And it's not just harming your studies, it's affecting your personal and professional life. Look around you. The modern world is a distraction machine. The phone buzzes every second. Notifications pull your focus. Pleasures are always one click away. We are surrounded by invisible obstacles that may seem harmless, but destroy your ability to concentrate. In ancient times, humanity's biggest challenges were war, hunger, disease. People had to fight to survive, endure the cold, and protect themselves from danger. Today, most of us don't face those threats daily. Our war has changed. Our battle is no longer against hunger or armed enemies. Our battle today is against social media that hijacks your attention, against the endless stream of stimuli that addict your mind, against the instant pleasures that kill your discipline. And you know what's even more dangerous? The modern world doesn't just rely on your natural weaknesses, it was designed to exploit them. The algorithm is working against you. It watches every click, every second you spend scrolling, every tiny pause of curiosity. And what does it do with that information? It feeds you exactly what it knows will hook you. It recommends what makes you procrastinate, what distracts you, what keeps you glued for hours without building anything meaningful inside of you. This is the silent war that most people never even notice. So how can you expect to have discipline to study, to work, to create, if every single click on what distracts you weakens your ability to stick with the things that require effort? The real enemy is not the complexity of what you want to learn. It's the simplicity of what pulls you away from it. The algorithm is like an equation engineered to exploit your curiosity against you. And the only way to win is to do the opposite, to consciously choose what you expose your mind to, the way a scientist chooses the data he allows into his experiment, because distraction is one of the greatest battles of modern life. So how do you break this cycle? How do you escape this invisible trap that trains your mind every single day to get distracted? Listen carefully. The key is not to eliminate social media completely. The key is to redirect it, because the same platform that weakens you today can also be used to strengthen you. Instead of clicking on everything that gives you cheap pleasure, start seeking content that elevates you, teaches you, and strengthens you. Bit by bit, the algorithm will adapt. It will begin recommending what feeds your mind instead of what drains your energy. Simple? Yes. But almost nobody has the discipline to do it. And here's the powerful truth. You don't need to abandon social media entirely. You need to transform it into a training ground. Instead of following pages that only distract you, follow mentors, follow thinkers, follow people who share ideas that expand your vision. Instead of consuming passively, turn every video into a starting point. Take notes, explain it out loud, apply it in practice. Don't fight against curiosity, direct it. The mind will always seek stimulation. Your power lies in choosing which kind. The secret is not to kill this instinct, but to guide it. If you direct your curiosity toward content that nourishes instead of drains you, you begin to train the algorithm to work for you, not against you. If you flip the switch and decide that every click is a vote for the future you want, the very system that holds you back today will start to push you forward. That is the difference between being a victim of the algorithm and using it as an ally in building your success. But listen closely. It's not enough to simply understand the problem. You need a system, because if you keep relying on willpower alone, you will lose. You need structure, and all of this begins with discipline. Discipline is the key. Imagine this. Every day you wake up and you don't depend on motivation. You know exactly what to do, how long to focus, and how to apply what you've learned. That is the power of a daily focus system. The first thing you need to understand is this. The human brain cannot maintain absolute focus for hours on end. That's an illusion. Forcing yourself beyond your natural limit only creates frustration. The secret is not quantity, it's quality. So remember this formula: 40 minutes of deep focus, 10 minutes of intentional rest. That's the ideal cycle. 40 minutes is long enough to dive into a subject without exhaustion. 10 minutes is the pause your mind needs to recharge before the next round. Push too far, and your mind scatters. Rest too long, and you lose your rhythm. But it's not just about setting time. It's about clearing the ground before you begin. Ask yourself, what is distracting me every day? It could be your phone, an open social media tab, or even a cluttered desk. Each of these is a silent thief of energy. And here's the truth. Every time you let a distraction into your space, your mind learns that it doesn't have to respect focus. You are training yourself to be distracted. So, rule number 1, your phone stays out of the study environment, not in your pocket, not face down on the desk, out of the room. If you need it as a tool, use apps that block notifications and limit access to distractions. Rule number 2, a clean desk. Everything in your field of vision competes for attention. Keep only what you'll use for that block of study. This signals to your brain that there are no escape routes. Rule number 3, focus questions. Before starting each cycle, write on a sheet of paper, what exactly do I want to understand in this block? This eliminates vague studying, the kind where you turn pages aimlessly. Clarity is the trigger for focus. Now, during those 40 minutes, practice something almost nobody does: active attention. That means not just reading, but engaging with the material. Take notes, ask questions, create examples. And when your mind starts to wander, and it will, don't fight the thought. Simply jot it down on a piece of paper. Distraction, pay the bill, call someone back, and then return. That simple act frees your mind because it realizes it doesn't need to hold on to that thought. During those 10 minutes of rest, don't make the fatal mistake of opening social media. That destroys the cycle. Rest must be active. Stand up, drink some water, walk around, stretch. This sends oxygen to your brain and signals that you're taking care of your body while your mind organizes what it just absorbed. And here's a detail almost nobody talks about. It's not only about how long you focus, it's also about what you cut. If you're losing hours every day to the same kind of distraction, you need to realize that it's not just a pastime, it's an addiction. Pay attention to the patterns. Which app do you open most? At what time of day? And what emotion triggers the escape? Is it boredom? Anxiety? Fear of not understanding? When you identify the trigger, you can cut the problem at the root. And here's a truth that can change everything. You don't need to be perfect. You need to be consistent. If you simply do 3 blocks of 40 minutes a day with proper breaks and strong boundaries against distractions, in 1 month you'll produce more than most people do in 6. Pay close attention to me now. Focus is not magic, it's engineering. It's the way you design your environment, your cycles, your habits, so that distraction doesn't even get a chance. If you're dominated by it today, it's not because you're weak, it's because you haven't built the right system yet. Build that system, and your mind will start to obey like a precise instrument, ready to take you to extraordinary results. But none of it matters if you don't have discipline. Knowing focus techniques, study cycles, or learning strategies means nothing without it. Focus is like a flame. You can light it today, but without discipline it will be gone tomorrow. Discipline is the daily fuel that keeps that flame alive until knowledge is finally turned into results. Discipline means doing what must be done even when you don't feel like it. It's sitting down to study when your mind craves distraction. It's completing the 40-minute block when everything inside you wants to quit. It's explaining out loud what you just learned even when nobody is there to listen. It's repeating until your mind understands that there's no negotiation. And here's the hard but liberating truth. Discipline is not prison, it's freedom. Because while most people live enslaved by distractions, impulses, and moods, the disciplined person is free. Free to choose what to learn. Free to build the future they want. Free from depending on luck or outside circumstances. Now imagine what happens when you bring the 2 pillars together. Trained focus and unshakable discipline. You don't just learn faster. You become someone who cannot be shaken. who doesn't sabotage themselves, who moves forward every single day despite criticism or difficulty. And it is exactly this consistency that the world rewards, with opportunities, with respect, with prosperity. In the end, it's not just about studying better. It's about building a mind so strong and so disciplined that no distraction can stop you. And when you reach that level, you'll realize something extraordinary. Success in any area of your life is no longer a matter of luck. It's only a matter of time. And the real power doesn't come from bursts of motivation, but from becoming methodical. The human mind responds to patterns, to repetition, to system. When you plan your study routine and decide exactly what you're going to do, you leave no space for excuses. You take away the burden of deciding and leave only the task of executing. And here's the key: start small. Don't try to become a genius in a single week. If today you can study for 15 minutes with full attention, start with 15. Tomorrow, push it to 20, then 30. The size of the step doesn't matter, the consistency does. What trains your mind is not the intensity of a single day, but the discipline of repeating every day until your mind learns to obey. Be methodical. Set the time, the place, the duration, and the specific goal. Don't just sit down to study anything. Write down, today I will understand this chapter, this concept, this technique. That creates a mental contract. And when you honor that contract, your mind begins to trust you. It realizes that when you say, I will, you follow through. And that's when self-confidence is born. Imagine this. Within a few weeks, you won't even need to struggle so hard to concentrate. Your mind will enter study mode almost automatically because you've trained it. You've taught your brain that there is a specific time of day when there are no negotiations, no distractions, no excuses, only commitment. That is the invisible force that turns ordinary people into extraordinary ones. Commitment means honoring what you planned, even when you don't feel like it. And that's exactly what shapes your identity. Every time you complete a daily goal, no matter how small, you send a powerful message to yourself. I control my mind, not the other way around. That is true freedom. Not doing things only when you feel like it, but because you decided. And the most impressive part is the compound effect. Small blocks of study, repeated day after day, create an exponential growth curve. What once seemed impossible to learn begins to feel simple. What used to take great effort becomes natural, because the mind, when trained, learns to obey. So remember this: the secret is not short bursts of intensity, it's method. It's not starting huge, it's starting small and never failing. When you become methodical, when you create a clear routine and stick to it, you'll realize there's no limit to what you can learn. Success in any area of life becomes nothing more than an inevitable consequence. Now it's your turn to act. Write in the comments, I have focus. That simple phrase will reprogram your mind to believe what you declare. And every time you repeat it, you strengthen your commitment to success. And remember, focus is the key, but positivity is the fuel. A positive mind finds solutions where others only see problems. Before you leave, hit the like button and subscribe to the channel.
If you were standing at arm's length from another person, just a normal distance, and each of you had just 1% more electrons than protons in your body, just 1 tiny percent of imbalance, the repelling force between you two would be enough to lift the weight equal to the entire Earth. Not a building, not a mountain, the whole planet. That's how ridiculously strong the electrical force really is. And this force is inside every single atom in your body right now, in everything you've ever touched or seen or will ever encounter. So why isn't everything exploding? Why aren't you being torn apart by these tremendous forces? See, all matter, everything, is a mixture of positive protons and negative electrons attracting and repelling with this enormous force. But so perfect is the balance, so incredibly precise is the arrangement, that when you stand near someone else, you don't feel any force at all. The positives and negatives are mixed together so finely, so intimately, that they cancel out almost perfectly. If you have a bunch of positive charges by themselves, they repel each other with tremendous force and spread out in all directions. A bunch of negatives would do exactly the same thing. But if you mix them together evenly, something beautiful happens. The opposite pieces get pulled together by the enormous attractions, and the net result is that these terrific forces balance themselves out almost perfectly by forming tight, fine mixtures of positive and negative. That's what matter is. That's what you are. A perfect balance of enormous forces, just sitting there, waiting. You know atoms have a nucleus at the center, right? This heavy, dense core made of protons and neutrons. And around it you have electrons, which are light and carry negative charge. The protons are positive, the electrons are negative. Opposite charges attract. So why don't the electrons just fall straight into the nucleus? Why don't they collapse right onto the protons and stick there? If the electrical force is so tremendously strong, what's keeping them apart? This is where things get genuinely interesting. The answer has nothing to do with electricity at all. It's quantum mechanics. See, there's this principle called the uncertainty principle that says you cannot know both where something is and how fast it's moving at the same time. The more precisely you pin down the position, the more uncertain the momentum becomes. Now, if you try to confine electrons into a very small space, very close to the protons, then according to this principle, they would have to have enormous momentum. They'd have to move incredibly fast. The more you squeeze them in, the more they jiggle around. And that jiggling, that motion required by the laws of quantum mechanics itself, is what keeps the electrical attraction from bringing the charges any closer together. It's like trying to trap something very energetic in a smaller and smaller box. The smaller the box, the more frantically it bounces around. Electrons do exactly this. You squeeze them, they move faster, and that motion keeps them from collapsing into the nucleus. So atoms have this structure, this size, because of a balance between electrical attraction pulling in and quantum mechanical motion pushing out. But now here's where things get really puzzling. What about the nucleus itself? Inside that tiny nucleus you have protons, multiple protons in most atoms, and they're all positive. Positive charges repel positive charges with incredible force, remember? So why don't all those protons just push each other away? Why doesn't every nucleus in the universe simply blow itself apart? Well, it turns out there's another force in nature, a force we don't experience in everyday life. It's called the nuclear force, and it only acts inside the nucleus, only over very, very short distances. And this nuclear force is stronger than the electrical force, strong enough to grab those protons and hold them together despite their electrical repulsion. The nuclear force has a very short range. It falls off incredibly rapidly with distance. The electrical force decreases with the square of the distance, 1 over r squared. But the nuclear force drops off much, much faster than that. So the nuclear force only acts between particles that are practically touching, between each proton or neutron and its immediate neighbors. Meanwhile, the electrical force reaches across the entire nucleus. Every proton repels every other proton, not just its neighbors, all of them. Think about how nature assembles atoms. Hydrogen has just one proton, the simplest thing there is. Helium has 2 protons and 2 neutrons, incredibly stable, one of the most tightly bound nuclei you can find. As you move up the periodic table, nuclei get bigger, more protons, more neutrons. And the nuclear force handles everything beautifully because all the particles are close together, all of them within reach of each other's grip. But as you keep adding protons, the nucleus gets bigger. And now you start having protons on opposite sides of the nucleus. They can barely feel each other's nuclear attraction because that force has such short range. But they still feel the full electrical repulsion. The more protons you add, the worse this imbalance gets. The electrical repulsion keeps building up, adding contribution from every single proton, while the nuclear force only connects nearest neighbors. Now, most nuclei find a way to balance this. They add neutrons, which contribute to the nuclear force without adding to the electrical repulsion, since neutrons have no charge. That helps stabilize things. But there's a limit. Eventually, you get nuclei that are so big, with so many protons, that the balance becomes incredibly delicate. The nucleus is holding together, but just barely, like a structure that's been stressed almost to its breaking point. And here's what's remarkable. That delicate balance, that tension between the nuclear force holding things together and the electrical force trying to push things apart, that's where the energy is. That's where the power is hiding. All that electrical repulsion that's being constrained, being held back by the nuclear force, that represents stored energy, tremendous amounts of energy. See, when you have positive charges pushed close together against their will, it takes energy to keep them there. It's like compressing a spring. The spring wants to expand. It's being held compressed, and that compression stores energy. The nucleus of a heavy atom is exactly like that. All those protons want to fly apart. The nuclear force is holding them together. And that tension, that compression, represents an enormous amount of stored electrical energy. Now, in stable atoms, this energy just sits there. It's locked away, inaccessible, part of the structure of matter itself. You can't get to it through chemistry, through burning things or mixing chemicals, because all of that only involves the electrons on the outside of atoms. The nucleus sits in the center, untouched by ordinary chemistry. That's why chemical energy and nuclear energy are in completely different categories. Chemical reactions rearrange electrons. Nuclear changes involve the nucleus itself, where these enormous forces live. The energy stored in a single nucleus is tiny in absolute terms, but there are astronomical numbers of atoms in any piece of matter. And per atom, per unit of mass, the energy locked in nuclear structure is millions of times greater than the energy available from chemical bonds. That's not an exaggeration, that's the actual ratio. Millions of times more energy hiding inside the nucleus than you can ever access through chemistry. And this is what's so beautiful about understanding atoms. You start with simple ideas. Positive attracts negative. Like charges repel. The nuclear force holds things together at short range. And from just those ingredients, you get all of chemistry, all of matter, and this hidden reservoir of power locked inside every atom. The Empire State Building stands rigid in the wind because electrical forces hold every electron and proton more or less in its proper place. The stiffness of steel, the hardness of diamond, the fact that you don't fall through your chair, all of this is electrical force at work. And it's the same force, the exact same electrical force, that represents such tremendous stored energy inside heavy nuclei. We live our whole lives surrounded by this power, and we never notice it. The balance is so perfect, so complete, that matter just seems solid and stable and boring. You pick up a piece of metal, and it's just a piece of metal. You don't feel the astronomical forces holding every atom together. You don't sense the energy locked inside. Every atom around you is a balance of tremendous forces, a structure held together by the interplay of electricity and quantum mechanics and the nuclear force. And inside that structure is stored the energy that powers stars. The sun doesn't burn like a fire. It doesn't get energy from chemistry. It gets energy from nuclear changes, from that reservoir of power locked inside atomic nuclei. The same physics that makes stars shine, that powers the entire universe, is sitting inside the atoms in your own body right now. Not doing anything, not releasing energy, just sitting there in perfect balance. But it's the same physics, the same forces, the same stored energy. When people first started understanding this in the early 20th century, it was genuinely shocking. Matter, ordinary matter, contains within it energy on a scale that was previously unimaginable. A tiny amount of matter, if you could somehow access that nuclear energy, represents more energy than enormous amounts of chemical fuel. The nuclear force has short range. Heavy nuclei are under tremendous internal stress. That's it. From those simple ideas, you can understand why matter contains such power, why the universe runs on nuclear energy, why stars shine for billions of years. The power hidden inside an atom isn't mysterious or magical. It's the electrical force, the most familiar force in the world, the force that makes lightning and static cling and holds molecules together. It's just that inside the nucleus, this force is compressed, constrained, held in check, and that compression represents energy, enormous energy. Now you might think, okay, I understand there's a lot of energy hidden in atoms, but how does it actually work? What's really happening inside there? And this is where we need to think more carefully about what an atom actually is. See, most people picture an atom like a tiny solar system. You've got the nucleus in the middle, like the sun, and electrons orbiting around it like planets. It's a nice picture, very intuitive, but it's wrong. The electrons aren't orbiting in nice circular paths. They're more like a cloud, a probability cloud, spread out around the nucleus. And they're constantly jiggling, constantly moving, because of that quantum mechanical principle I mentioned. They can't sit still. If they sat still, we'd know exactly where they are and how fast they're moving, which is zero. And that's not allowed. The universe literally forbids it. So electrons have to keep moving. They have to maintain this minimum amount of motion even at absolute zero temperature. Even if you cooled something down as far as physics allows, the electrons would still be jiggling. That's not heat. That's not thermal energy. That's just the quantum mechanical requirement for existence. The universe says you must keep moving, and so they do. Now the nucleus is a completely different story. The nucleus is tiny compared to the atom, incredibly tiny. If you took an atom and magnified it until it was the size of a large room, the nucleus would be a speck you could barely see with your eye. Almost all of the atom is empty space with this diffuse electron cloud, but almost all of the mass is in that tiny speck at the center. Inside that speck, you have protons and neutrons packed together with incredible density. A teaspoon of pure nuclear matter, if you could somehow get it, would weigh millions of tons. That's how tightly packed things are in there. And holding all of that together is the nuclear force, fighting constantly against the electrical repulsion of all those protons. What matters is this balance I keep talking about. The nuclear force attracting, the electrical force repelling, and the structure that emerges from their competition. In small nuclei, the nuclear force wins easily. Helium is incredibly stable, very tightly bound. The 4 particles in there, 2 protons and 2 neutrons, are arranged in a way that's almost perfect. But as nuclei get bigger, something changes. The electrical repulsion keeps adding up, while the nuclear force can only do so much. Think about it this way. If you're a proton sitting in the middle of a large nucleus, you feel the nuclear force from your immediate neighbors, the particles right next to you. But you feel electrical repulsion from every single other proton in the entire nucleus, even the ones far away on the other side. For a small nucleus, this isn't a big deal. There aren't that many protons, and they're all pretty close together. But for a large nucleus, with dozens of protons, the electrical repulsion adds up to something substantial. Each proton is being pushed by all the others, and the nuclear force, strong as it is, only reaches so far.
So large nuclei are under stress, internal stress. They're holding together, but there's this constant tension between the force trying to keep things together and the force trying to push things apart. This is why the periodic table ends where it ends. It's not arbitrary. You literally cannot make stable atoms beyond a certain size because the electrical repulsion becomes too much for the nuclear force to handle. The heaviest stable element is lead with 82 protons. Everything heavier than that is unstable to some degree. Take uranium with 92 protons. 92 positive charges all crammed together, all repelling each other. The nuclear force is holding on, but just barely. The balance is so delicate that the nucleus is almost ready to fly apart from the electrical repulsion alone. Now, what does it mean for a nucleus to fall apart? Well, there are different ways it can happen. Sometimes a nucleus just ejects a small piece of itself, a little cluster of 2 protons and 2 neutrons, which is actually a helium nucleus. This is called alpha decay. The nucleus is too big, too stressed, so it throws out a chunk and becomes smaller and more stable. Sometimes a neutron inside the nucleus transforms into a proton, or vice versa, emitting other particles in the process. This is beta decay. The nucleus is adjusting its composition, trying to find a better balance between protons and neutrons. And sometimes, for very heavy nuclei like uranium, if the nucleus is just tapped lightly, if you send in a slow neutron, just give it a tiny nudge, it can't hold together anymore. It breaks. It splits into 2 large fragments, each with positive charge. This is fission. And what do positive charges do? They repel with enormous force. So those 2 fragments fly apart at tremendous speed, pushed by all that electrical energy that was being held in check. And here's the key insight. Medium-sized nuclei are more stable than very large ones. They're in a lower energy state. The protons in a medium-sized nucleus don't feel as much total electrical repulsion because there aren't as many protons to repel them. So when a large nucleus splits into 2 smaller ones, the final state has less stored energy than the initial state. And that difference in energy has to go somewhere. It goes into motion. The 2 fragments fly apart at tremendous speed. That's kinetic energy. That's heat. That's the energy release. And here's what's beautiful about this. The energy comes from electricity. It's the electrical repulsion that drives the fragments apart. The nuclear force was holding things together, keeping all that electrical potential energy stored up. And when the nucleus splits, the nuclear force can no longer constrain the electricity. The positive charges push each other away with all that force we talked about at the beginning, and the fragments fly apart. So nuclear energy is really electrical energy, It's the electrical energy that was stored in keeping all those positive charges close together against their will. When you release that constraint, when the nucleus breaks apart, the electrical repulsion converts that stored potential energy into kinetic energy, into motion, into heat. The amount of energy involved is staggering. Each nuclear reaction releases millions of times more energy than a chemical reaction. Millions of times. And this isn't because nuclear forces are somehow magical. It's because the electrical force is so incredibly strong when you're dealing with charges that close together. Inside a nucleus, the distances are tiny, femtometers, millionths of a billionth of a meter. At those distances, the electrical force between protons is enormous. Now, there's another way to get nuclear energy, and it's sort of the opposite of what I just described. Instead of splitting heavy nuclei apart, you can push light nuclei together. This is fusion, and it actually releases even more energy than fission. How does that make sense? If splitting things releases energy, and combining things also releases energy, where's the energy actually coming from? The answer is that middle-sized nuclei are the most stable. Iron, with 26 protons, is about the most tightly bound nucleus you can make. It's at the bottom of the energy valley. So if you start with something heavier than iron and split it, you release energy by moving toward that stable middle. And if you start with something lighter than iron and combine it, you also release energy by moving toward that stable middle. Either way, you're going downhill toward iron. Fusion is what powers the sun. Hydrogen nuclei, just single protons, are being pushed together so hard that they overcome their electrical repulsion and get close enough for the nuclear force to grab them. And when that happens, when they fuse together, the resulting nucleus is in a lower energy state than the separate particles were. That difference in energy is released as light and heat. The sun is converting hydrogen into helium, moving from the lightest elements toward that stable middle and releasing energy in the process. It's been doing this for about 5 billion years. And it'll keep doing it for another 5 billion before it runs out of hydrogen fuel. That's how much energy is stored in those light nuclei, enough to power a star for billions of years. And the elements heavier than iron, where do they come from? They actually require energy input to create. They're made in supernova explosions when dying stars release so much energy that they can push nuclei past iron up the energy hill rather than down. Every atom of gold or uranium in the universe was created in the violent death of a star. So the energy hidden in atoms connects to everything. It's why stars shine, why the sun warms the earth, where the elements came from. All of it traces back to this balance of forces inside the nucleus, this tension between electricity trying to push things apart and nuclear force trying to hold things together. The thing that gets me about all of this is how ordinary it seems from the outside. You look at a piece of metal, a rock, a glass of water, and it just sits there, completely still, completely boring. But inside, at every moment, there's this incredible drama playing out. Forces pushing and pulling, particles jiggling, energy stored and balanced with such precision that the whole thing appears motionless. And the numbers involved are just staggering. A single gram of matter contains something like 1 trillion atoms. Each one of those atoms has a nucleus, holding protons together against their electrical repulsion. Each one has electrons maintaining their quantum mechanical dance around the outside. And all of it is happening right now, constantly, everywhere, in everything. That's the thing about nuclear energy. It's isolated from everyday physics. Chemical reactions shuffle electrons around. Heat makes atoms jiggle faster. But the nucleus just sits in the center of it all, completely indifferent. It takes something much more dramatic to affect what's happening in there. You need particles with enough energy to actually penetrate to the nucleus. This is why nuclear physics was discovered so late in the history of science. Electricity was understood in the 1800s. Chemistry was well developed. But nuclear physics had to wait until the 20th century because you need special tools to probe something that small and that well protected. The first hint that something was going on inside atoms came from radioactivity. People noticed that certain materials emitted invisible rays that could fog photographic plates and make air conduct electricity. This was completely mysterious at first. Where was this energy coming from? The materials weren't connected to anything. They weren't being heated or stimulated. They were just sitting in a drawer, emitting energy year after year. It took decades to figure out that the energy was coming from inside the atoms themselves. The nuclei of certain elements were unstable, and occasionally one would transform, releasing a burst of energy in the process. Not chemical energy, something else entirely. Something from deeper inside the atom than anyone had previously imagined. And when people finally understood what was happening, when they realized how much energy was stored in nuclear structure, it changed everything. Ordinary stuff, the rocks and metals and water we'd been living with forever, turned out to contain power on a scale that was previously unimaginable. A single kilogram of matter, if you could convert all of its mass to energy, contains the equivalent of millions of tons of chemical fuel. Millions of tons from 1 kilogram. Now, you can't actually convert all the mass to energy through nuclear reactions. You only release a tiny fraction of the total. But even that tiny fraction is enormous compared to anything chemistry can provide.
I want you to do something for me. Right now. Look around this room. On, pause, gesture around, on. No, really. Look around. Look at the lights. Look at the walls. Look at the person sitting next to you. Look at your own hands. Now ask yourself, do you actually see what you're looking at? Let that question hang. I mean, really see it. Do you know why the lights work? Do you understand why the walls stand up? Do you know what's happening inside the cells of your skin right now? Most of us walk through the world half blind. We see things, but we don't really look at them. We accept things, but we don't question them. We experience things, but we don't wonder about them. We've lost something that every child has naturally, something that most adults trained out of themselves somewhere around 3rd grade. Hum non and fe curiosity. Not the shallow, I wonder who won the game, curiosity. I'm talking about deep, relentless, almost childlike curiosity about how things actually work, about why things are the way they are, about what would happen if things were different. Richard Feynman never lost that. And that, more than his intelligence, more than his education, more than any other factor, is what made him a genius. Today, I'm going to tell you about Feynman's curiosity rule. The principle he lived by that transformed him from a smart kid in Queens into one of the most revolutionary minds in science. And more importantly, I'm going to show you how you can apply that same rule to your own life. Because here's the secret: genius isn't born, it's cultivated. And curiosity is the cultivation process. I'll walk across stage. Let me tell you a story. It's 1918. Feynman is born in Queens, New York, working class family. Nothing special. His father sells uniforms. His mother is a homemaker. No PhDs in the family, no famous scientists, just regular people. But Feynman's father does something different, something most parents don't do. He doesn't answer questions with answers. He answers questions with more questions. Little Richard asks, "Dad, why do the balls roll downhill?" Most parents would say, "Because of gravity, honey. Now finish your dinner." Not Feynman's father. He says, "Well, why do you think they roll downhill? What do you notice about things that roll? What happens if you try to roll something uphill?" Act gesture. He's not giving Richard facts to memorize. He's teaching him how to be curious, how to observe, how to question, how to think. And here's the key moment, the moment that shapes everything that comes after. Young Feynman is lying in his wagon, and his father is pulling him along the sidewalk. And suddenly, the father stops. The wagon jerks forward, and a ball that was sitting in the wagon rolls to the front. "Did you see that?" his father asks. "Yeah, the ball rolled forward when we stopped. Why do you think that happened?" And right there, at maybe 5 or 6 years old, Feynman starts thinking about inertia. Objects in motion stay in motion. He doesn't know the word yet. He doesn't know the physics. But he's experiencing it, questioning it, wondering about it. This is the curiosity rule. Not just asking questions, but teaching yourself to see the world as a series of fascinating mysteries waiting to be explored. And Feynman never stopped doing this. Ever his entire life, he looked at the world like a 5-year-old in a wagon, noticing things that everyone else ignored. Let me show you what this looked like in practice. If Fair share this story with energy, it's the 1940s. Feynman is at Los Alamos working on the atomic bomb. The stakes couldn't be higher. The stress is incredible. They're working 16-hour days doing complex calculations that, if wrong, could literally blow everyone up. And what does Feynman do in his spare time? He learns to pick locks, not because he needs to, not because it's useful for the project, but because he's curious. How do locks work? What's the mechanism? Can he figure it out? So he gets a book on lockpicking. He practices. He experiments. And pretty soon he's breaking into filing cabinets all over Los Alamos. Not to steal anything, just to prove he could do it. He'd leave notes saying, "Guess who was here?" Karslov security is furious. But Feynman is delighted. Because he's learned something new, he's satisfied his curiosity. But here's what's interesting. This isn't a distraction from his real work. This curiosity, this relentless need to understand how things work, is exactly what makes him brilliant at physics. Because physics isn't about memorizing formulas. It's about understanding how the universe works. And you can't do that unless you're genuinely, deeply curious about it. A walk to other side as, let me tell you another story. This one's even better. Feynman wins the Nobel Prize in 1965. He's at the top of his field, famous, respected, secure in his position at Caltech, and he gets depressed. Yeah, seriously, Nobel Prize winner depressed. Why? Because physics has stopped being fun. It's become about reputation, about publishing papers, about being taken seriously, about defending his ideas, about politics. The curiosity is gone, and without curiosity, even physics, even winning a Nobel Prize, feels empty. Has slowed down here. So one day, he's in the Caltech cafeteria, and he sees a student throw a plate in the air, and the plate wobbles as it spins. The Caltech logo on the plate seems to rotate faster than the plate itself, and Feynman thinks, that's interesting. I wonder what the relationship is between the wobble and the spin, a gesture, the motion. So he goes back to his office, and just for fun, not because anyone asked him to, not because it'll lead to a publication, just because he's curious. He works out the physics of a wobbling plate. He derives the equations. He figures out the relationship. It's a 2-to-1 ratio. For every complete wobble, the plate spins twice. And he shows it to a colleague, excited about what he's discovered. The colleague says, "That's nice. But so what? What's the importance of this?" And Feynman says, "It has no importance. I'm just playing around." A pause. Let this land. But here's what happened next. That playful curiosity, that willingness to explore something just because it was interesting, led him back into the heart of quantum physics. The wobbling plate problem connected to rotation in quantum mechanics, which connected to his work on quantum electrodynamics, which was the work that won him the Nobel Prize. The curiosity saved him. The play saved him. The willingness to explore something for no reason other than, I wonder, saved his career and his sanity. Sir, direct statement? This is the curiosity rule. Follow your genuine interest even when it seems pointless. Especially when it seems pointless, because you never know where curiosity will lead you. And the connections you make, the insights you gain, the understanding you build, they compound in ways you can't predict. Now, I know what you're thinking. That's great for Feynman. He was a physics professor. He could afford to play around. But I have a real job. I have responsibilities. I don't have time for curiosity. Let me tell you why that's exactly backwards. Get passionate at curiosity isn't a luxury. It's not something you do after you've handled all your responsibilities. It's the thing that makes you better at your responsibilities. Let me give you some examples from people who aren't Nobel Prize winning physicists. Steve Jobs was obsessed with calligraphy. He'd audit calligraphy classes at Reed College. He'd spend hours studying different typefaces. People thought he was wasting his time. But that curiosity about fonts and design, that's why the Mac had beautiful typography. That's why Apple products have always prioritized design. That curiosity, which seemed pointless, created billions of dollars of value. Another example, Leonardo da Vinci was curious about everything. How do birds fly? How does water flow? How do muscles attach to bones? What happens when you smile? He'd spend months just observing, drawing, questioning. People thought he was procrastinating. They wanted him to focus on his commissions. But that curiosity, that relentless observation of everything, is why his art is timeless. The Mona Lisa smile works because Da Vinci understood facial anatomy better than any artist before him. His flying machine designs came from understanding birds. His hydraulic engineering came from observing water. The curiosity wasn't a distraction from his work, it was his work. And here's what's crucial. This principle applies to everyone, not just artists and scientists. Everyone. You're a teacher. Curiosity about how different students learn will make you better at teaching. You're a salesperson. Curiosity about why people buy and why they don't will make you better at sales. You're a parent. Curiosity about how your kids think will make you better at parenting. You work in IT. Curiosity about why systems fail will make you better at preventing failures. Walk across stage, curiosity is the universal skill. The meta skill. The skill that makes every other skill better. But here's the problem, most of us have had our curiosity trained out of us. Think about it. When you were a kid, you asked why? Constantly, why is the sky blue? Why do we have to sleep? Why can't I have ice cream for dinner? Why? And what happened? Adults got tired of your questions. Because I said so. That's just how it is. Stop asking so many questions. Asex voice getting serious. Then you went to school. And school didn't reward curiosity, it rewarded compliance. Sit still. Be quiet. Memorize this. Regurgitate that. Don't question. Don't explore. The curious kids, the ones who kept asking why. They were labeled as problems, troublemakers, distractions, and slowly, systematically, we learned to stop being curious. We learned that curiosity is inappropriate, childish, a waste of time. By the time we're adults, most of us have had our curiosity beaten out of us entirely. We accept things without questioning them. We follow procedures without understanding them. We live on autopilot. Pausas, and then we wonder why we're bored, why we feel stuck, why life feels empty. It's because we killed our curiosity. And without curiosity, life is just existing. Feynman never let that happen. He protected his curiosity like it was the most precious thing in the world. Because it was. Let me tell you how he did it.
Teaching modus.
Feynman had this rule: everything is interesting if you look at it closely enough. Everything, not just physics, not just science, everything. He'd be at a bar, and he'd get curious about why the ice cubes crack when you pour whiskey over them. Thermal shock, dissolved gases. He'd work it out. He'd be walking down the street and see ants. How do ants know where to go? Do they leave chemical trails? How do they communicate? He'd go home and read about ant behavior. He'd watch a magician and get curious about the psychology of misdirection. How do magic tricks work? What makes us miss the obvious? He'd study magic and even perform some tricks himself. Hard gesture widely bongos, safe cracking, drawing, biology, computing, art, music, languages. He was curious about all of it, and people would ask him, why do you spend time on these random things? You're a physicist. Shouldn't you focus? And he'd say, I am focusing. I'm focusing on being curious. And curiosity doesn't have borders. It's pausing. This is the key insight. Curiosity isn't about knowing everything. It's about being interested in everything. You don't have to master everything you're curious about. You just have to be willing to explore, to ask questions, to wonder. Because every time you satisfy one curiosity, you develop your ability to be curious. You strengthen that muscle. You build that habit. And that habit, that reflex of looking at the world and asking, I wonder why. That's what makes you a genius. Not because you know more facts than everyone else, but because you see connections that everyone else misses. Because you ask questions that everyone else doesn't think to ask. Because you understand things at a deeper level. Now let me give you the practical framework. How do you actually live by the curiosity rule? Present this clearly. First, notice what you notice. This sounds simple, but it's profound. Start paying attention to the things that catch your attention. You're walking down the street and you notice a building. Don't just walk past it. Stop. Ask yourself, what caught my attention? The shape, the color, the architecture. That moment of noticing, that's your curiosity talking. Listen to it. Feynman did this constantly. He'd notice things that everyone else walked past. A reflection in a window, the pattern of cracks in a sidewalk, the sound of a car engine. And he'd stop, he'd look, he'd wonder. Second point, ask the next question. When you notice something interesting, don't just file it away. Ask the next question. That's an interesting building. Why is it shaped that way? When was it built? What purpose does that design serve? That's a weird sound the car is making. What's causing it? Is it a problem? How does that part of the engine work? The first question is curiosity. The second question is cultivation. Our third point. Actually try to answer your questions. Don't just wonder, investigate. You don't have to spend months researching everything. Sometimes it's a 5-minute Google search. Sometimes it's asking an expert. Sometimes it's a quick experiment. But do something. Take action on your curiosity. Feynman would see a question and immediately start playing with it. Drawing diagrams, working out math, building models. He didn't just think about things, he engaged with them. A fourth point for fourth, follow the connections. One curiosity leads to another. Follow the thread. See where it goes. You get curious about why coffee tastes different depending on brewing method. That leads to questions about extraction, which leads to chemistry, which leads to questions about molecular bonds, which leads to quantum mechanics. Suddenly, your curiosity about coffee has taught you chemistry and physics. Ask gesture the path. This is how Feynman worked. He'd start with something simple and follow the connections until he ended up somewhere profound. And the beautiful part is, you don't know where curiosity will take you. That's the point. The journey is unpredictable. And that unpredictability is what makes it valuable. Let me tell you about a time this happened to Feynman in a way that changed science. Share this story with building excitement. It's the late 1950s. Feynman is curious about biology. He's a physicist, but he wonders, how does biology work at the molecular level? So he starts attending biology lectures. He reads biology papers. He asks biologists questions. He's just curious. And the biologists are confused. Why is a physicist interested in biology? Shouldn't you stick to physics? But Feynman doesn't care. He's curious, so he's going to explore. And as he learns about DNA, about proteins, about molecular machinery inside cells, he starts seeing it through a physicist's eyes. He starts thinking about these biological processes in terms of information theory, in terms of quantum mechanics, in terms of thermodynamics. And he has an insight that biologists missed. Living systems are essentially tiny machines governed by the same physical laws as everything else. You can understand biology through physics. Positive, this insight, born from pure curiosity, helped launch the field of biophysics. It changed how scientists think about life itself. And it started because Feynman was curious about something outside his field, because he didn't respect the boundaries that everyone else respected. Our direct challenge. Now, here's my question for you. When's the last time you followed your curiosity across a boundary? When's the last time you explored something just because it was interesting? Not because it was useful for your job or required for your degree or relevant to your current project. When's the last time you let yourself be genuinely curious about something? A pause for most people, the answer is years, maybe decades. Maybe never as an adult, and that's tragic because curiosity isn't just about learning facts. It's about staying alive mentally. It's about maintaining wonder. It's about being engaged with the world instead of just going through the motions. Feynman was curious until the day he died. Literally, on his deathbed, dying of cancer, he was still asking questions, still wondering, still engaged. And he said something beautiful near the end. Someone asked him if he was afraid of dying. He said, "No, I've had a wonderful life. I got to play. I got to be curious. I got to see things and understand things. What more could you ask for?" If I let emotion come through, he didn't say, "I'm glad I published 100 papers," or "I'm glad I won awards." He said he was glad he got to be curious. That was what mattered to him, not the achievements, the curiosity that led to them. And I think that's the most important lesson here. AFAR, slow down. Success, real success, the kind that makes your life meaningful, doesn't come from grinding. It doesn't come from discipline. It doesn't come from following the rules. It comes from curiosity. When you're genuinely curious about something, you don't need discipline. You want to work on it. You're excited to work on it. It doesn't feel like work. When you're curious, you don't need external motivation. The curiosity itself is the motivation. When you're curious, you don't need to force yourself to learn. Learning happens naturally because you want to know. Get passionate. This is why curious people are successful. Not because they work harder than everyone else, though they often do, but because they're working on things they actually care about, things that genuinely interest them. And when you work on something you're genuinely curious about, you see things that other people miss. You make connections that other people don't make. You persist when other people give up, not because you're more disciplined, but because you want to know the answer. That's Feynman's secret. That's the curiosity rule. Don't force yourself to be interested in things that bore you. Find the things that genuinely spark your curiosity and follow that spark wherever it leads. Let me give you some modern examples of people who've done this. Amsar share contemporary examples that Elon Musk gets curious about physics and engineering. He starts asking, why are rockets so expensive? Why can't they be reusable? Why does everyone accept that space is only for governments? That curiosity leads to SpaceX, which changes the entire space industry. Sarah Blakely gets curious about why pantyhose are uncomfortable. She starts asking, why do they have seams? Why don't they stay up? Why can't they look better? That curiosity leads to Spanx, which becomes a billion-dollar company. Lin-Manuel Miranda gets curious about Alexander Hamilton. Who was this guy? What was his story? Why don't people know about him? That curiosity leads to reading the Hamilton biography, which leads to wondering, could this be a musical? Which leads to Hamilton, which becomes a cultural phenomenon. Point, none of these people set out to be successful. They set out to satisfy their curiosity. And the success was a side effect. That's how it works. Curiosity first. Success follows, not the other way around. You can't manufacture curiosity for the sake of success. You have to genuinely care about the questions. Now let me address something important. Some of you are thinking, I'm not curious about anything. Nothing interests me anymore. Empathize I hear this a lot, and I want to tell you that that's not true. You're still curious. You've just buried it under years of being told not to be. Let me help you find it again. Ere offer this gently. Think back to when you were a kid. What did you love? What could you spend hours doing without getting bored? Maybe you loved taking things apart. Maybe you loved drawing. Maybe you loved reading about dinosaurs. Maybe you loved making up stories. Maybe you loved building with Legos. Whatever it was, that was your curiosity expressing itself. And here's the thing, it's still there. You just stopped listening to it. So start listening again. What catches your eye when you're scrolling through social media? What makes you stop and read instead of just scrolling past? What do you find yourself thinking about when you're in the shower or driving or falling asleep? What topics make you light up when they come up in conversation? As our point, those are clues. Your curiosity is trying to tell you what it wants to explore. Listen to it. Follow it. Even if it seems silly. Even if it seems impractical. Even if it seems like a waste of time. Because here's what I've learned, and here's what Feynman proved with his entire life. Nothing that genuinely interests you is a waste of time. The time you spend following your curiosity is the most valuable time you'll ever spend, because it's the time when you're most alive, most engaged, most yourself. Let me tell you one final story about Feynman. This one really gets to the heart of the curiosity rule. Tell this with admiration. Feynman is in his 70s. He's had an incredible career. Nobel Prize, revolutionary discoveries, famous lectures, successful books. He could coast, he's earned it. But he doesn't coast, he's still curious. And he gets interested in computing. Not because he needs to. He can do all the calculations he needs by hand or with traditional computers. But because he's curious. How do computers actually work? What's the theory behind computation? So he starts learning about computer science. He reads Alan Turing. He studies algorithms. He plays with early computers. And then he gets curious about a specific question. Can computers simulate quantum systems? If quantum mechanics is the fundamental reality and computers operate on classical logic, can they ever truly model quantum behavior? This question, born from pure curiosity, leads him to invent the concept of quantum computing. Let that land at age 70, when most people are retired, when most scientists are coasting on past achievements. Feynman is still curious enough to invent an entire new field of science, because he never stopped asking, I wonder, walk to center stage. And that's what I want you to take from this. That's the lesson. That's the rule. Stay curious. Not because it'll make you successful, though it will. Not because it'll make you smarter, though it will. Not because it'll make you richer, though it might. But because curiosity is what makes life worth living. Final appeal. When you're curious, every day is interesting. Every conversation is an opportunity to learn. Every experience is a chance to discover something new. When you're curious, you don't get bored. You don't feel stuck. You don't wonder what the point is. Because the point is the curiosity itself. The wondering, the exploring, the discovering. That's what Feynman understood. That's what made him not just successful, but happy. Not just intelligent, but alive. And you can have that too. You can choose curiosity.
Right now?
Today? Direct instruction. Here's what I want you to do. Today, not tomorrow. Today. Find one thing that makes you curious. Just one thing. It doesn't have to be big. It doesn't have to be important. Maybe it's a question you've always wondered about. Maybe it's a skill you've always wanted to learn. Maybe it's a topic you keep meaning to explore. Whatever it is, spend 30 minutes on it. Just 30 minutes, not to become an expert, not to accomplish anything, just to explore, to wonder, to play. And notice how you feel. Notice if your mind wakes up a little. Notice if you feel more engaged, more alive. That feeling. That's what Feynman felt every day of his life. That's the curiosity rule in action. And if you like that feeling, if you want more of it, do it again tomorrow, and the next day, and the next. Build the habit of curiosity. Protect it, nurture it, let it grow, because that habit will change your life more than any other habit you could possibly develop. A pause. Let it breathe, Feynman once said. I learned very early the difference between knowing the name of something and knowing something. Most people spend their lives learning names, collecting facts, accumulating credentials, looking smart. Curious people spend their lives knowing things, understanding things, connecting things, being smart. Most point to audience A. Which one do you want to be? Someone who knows a lot of names, or someone who actually knows things, someone who looks successful, or someone who is successful because they're genuinely engaged with what they're doing, someone who exists, or someone who lives. Final pause, choose curiosity. Ask why more often. Notice what you notice. Follow what interests you. Play, explore, wonder. Be like Feynman, not because you want to win a Nobel Prize, though who knows, maybe you will, but because curiosity makes everything better. Everything. Your work, your relationships, your happiness. Curiosity is the rule. Everything else is just details. Or smile warmly, thank you. And be it, hey, if this sparked your curiosity about how one of history's greatest minds actually thought, if you want to explore more of Feynman's principles and how to apply them to your own life, do me a favor. Like this video and subscribe to the Mind of Richard Feynman channel. We're diving deep into the habits, techniques, and philosophies that made Feynman extraordinary. And I promise every video will give you something to be curious about. Join us. Let's stay curious together. See you in the next one.